Everyone's talking about GPUs and AI accelerators, but none of that works without a CPU at the center. And right now, the world's most advanced compute relies on cores designed by a company in my own backyard, ARM. ARM invited me to its headquarters and sponsor this video to help me answer a simple question. What exactly makes a good CPU today? Not a good CPU when the design started 5 years ago, not a CPU that exists solely in the mind of an engineer, but right now, for both data center and smart devices. Now right now, of course, we're in the middle of this AI era, where power budgets are tight, workloads are shifting fast, and time to silicon is everything. I went to ARM headquarters to find out where the decisions happen, which workloads get modeled, which trade-offs get made, and which features land in silicon, and which don't. These teams work closely with cloud providers, chip designers, and OEMs to produce something that can actually ship, and they all have to do it on a schedule inside this building. But cores are only part of the story. We're also talking to the people who design the systems around them, validate the software they'll run, and decide what the next generation of compute is supposed to look like. With any luck, they'll let us film inside the labs, and we might even get to interview an architect or two. I'll ask again, what exactly makes a good CPU? Now, ARM's place in modern compute didn't begin in the cloud. It began in smaller devices, and the first most of us realized was in the devices we keep in our hand or in our pocket, or on our table here. In the smartphone era, ARM is king. The smartphone has a number of constraints though, not just baseline performance, but devices have to be small, efficient, quiet, and run all day. In something like a smartphone, there is an extra thermal headroom. There's also no time for waste, given it's a consumer device. That created a different CPU design philosophy to the legacy model, one focused on both performance per watt and peak performance. And that mindset shaped everything. ARM built its CPUs around real-world use, not just what the synthetic benchmarks rewarded, but what users were actually doing. That means throwing out the Antutu or DMIPS tests and focusing on web browsing, messaging, photos, apps. As someone who has been testing hardware for almost 2 decades at this point, the delineation between synthetic and real-world tests matters. But it also means that year after year, ARM has launched new cores that have reflected how software is evolving. Every generation has been aimed at what came next, not what looked best on paper. That annual cadence has become part of the model, and still is. Today, more than 50 billion ARM CPUs ship every year, over 100 million ARM GPUs. The company's reach extends far beyond smartphones. I'm talking about smart TVs, wearables, cars, IoT, sensors, network infrastructure, dozens upon dozens of ARM-based notebook PCs, and now into the data center. CEO Rene Haas states that 50% of data center CPUs will be ARM-based sooner than most people realize. That combination of NVIDIA's Grace and hyperscalers' own designs. But that expansion didn't happen by accident. It came from sticking to the fundamentals. Things like efficiency, flexibility, and, as we'll see in this video, relevance to the software stack. Thing is, this is the important part. The world is full of bad cores. I've seen them be presented, and I've talked to the teams that built them. I've stood at Hot Chips watching an architecture slide for a different type of CPU and wondering what on earth were they thinking? A bad CPU isn't just slow, it's wasteful. It's out of step with the workload it's designed for. And once it's in production, it's way too late to fix. That's why I want to see what ARM does that's so different. Now, when you're designing a CPU, it's easy to get caught up in the headline numbers. We're talking things like just simple core count or frequency. But the modern CPU design lives in the trade-offs. We're talking power, performance, area, and time to market. Something in the industry we often call PPAT. Sometimes we add a C in there, PPAT-C, where C is cost. The thing is, these things don't move independently. You can't just keep turning one knob hoping the others stay fixed. Everything you change affects everything else. It was once described to me that designing a CPU is like having 1,000 degrees of freedom, but if you adjust one to make it better, 3 more get worse. And then it's a question of simply scale, scale, scale. But even that doesn't really capture how a CPU design works today, because design also has to consider the end device. One core design might go into a smartphone, another into a networking appliance, and then another into a hyperscale server with a stack of accelerators bolting onto the side. And sometimes, in all three, it's the same core. That means every design has to be built with a wide range of use cases in mind. You can't just design it for one customer or one market. You have to give everyone enough flexibility to shape the final system around the core without fighting against that system. That's harder than it sounds. You can't optimize for everything. For example, if the core is too wide, you burn area. If you chase frequency, you lose efficiency. Ultimately, the best design, from the IP perspective, is to build something balanced for the market and then make sure it integrates cleanly. It has to scale down when it needs to, and it has to scale up when customers demand more. If you're building a CPU for others to use, it has to fit inside platforms you didn't build with workloads you don't control. But the more you know, the better you can design. This is where real-world insight makes a difference. One of the benefits of being as big as ARM or having as many customers as ARM is that everyone in the ecosystem wants the cores to do better. As a result, they share both existing and upcoming workloads. ARM then builds an understanding of software from data, they model it at scale, they draw from real code bases, production systems, and feedback from those partners. The end result is something more suited to their customer base, especially when it comes to high performance. Now, don't get me wrong here, there's also the broader software stack to consider. The hardware has to align with the compilers, with the toolchains, operating systems, debuggers, and schedulers. The microarchitecture needs to reflect how the software stack behaves. If there isn't any alignment, performance can suffer and integration becomes harder. Optimization becomes even much harder. Ecosystem work is what keeps that from happening. If the tools are ready, the compilers are tuned, and the partners aren't forced to figure out on their own, then it can work. Then there's a schedule. Time to market matters just as much as power of performance. If a core shows up late, it doesn't matter how good it is. Products move on, and that's why predictability in cadence matters. If your customers can't rely on that, they will just simply look for another solution. That's the shape of modern CPU design. Peak performance has its place, but the design today is shaped by everything else around it. That process spans software, integration, and delivery. It only works when all are considered together, and you have to hold all of it in view at once. Now, ARM's design process follows this trend, and it starts with software. Inside the company, a dedicated team focuses on understanding how production code behaves across phones, infrastructure, consumer platforms, and high-performance compute. This work is done at scale. Workloads come in from across the entire customer base. This means some are commercial, some are open source, but others are built internally to highlight pressure points in the pipeline. Partners contribute traces, performance data, and trends from their own customer base. All of this feeds into ARM's architecture models, into the simulation frameworks, and the performance tools that run 24/7. The goal is to make architectural decisions with visibility into what the code is already doing and what is likely to do next. For example, does tweaking this cache make a difference? Does a wider decode engine on this core matter for a set of workloads? Or does it even make it worse, or better, or worse? In my discussions at headquarters, it's clear the team working on this doesn't just come from hardware backgrounds. Many of them are software engineers who have worked on compilers, kernels, operating systems, and toolchains. They know how to profile code flow through the system. That includes instruction mixes, memory access patterns, branch pressure, and everything else that shows up when a system runs real software in a real environment. That insight directly informs how these new cores are developed. When patterns emerge in how applications behave, the team can adjust any future architecture in a myriad of ways to see what makes them handle better. Decisions about width, depth, and issue logic aren't made in the abstract. They're grounded in what the software needs and what will allow partners to build competitive systems. That feedback loop doesn't end, even with designs in mind. ARM's largest partners engage, often taking those FPGA designs and comparing them to their internal data, and provide feedback. ARM then gets a clearer picture of how the core will be expected to perform, and the customers get earlier access to the performance envelope. In some cases, compiler flags and scheduling models are profiled years in advance to prepare for a new core's release. More recently, of course, machine learning has entered the design process as a tool. ARM embraces internal machine learning models as an assistive tool to explore these architectural trade-offs, to identify tuning opportunities, and to accelerate internal analysis. These tools are trained on a wide corpus of past designs and customer workload behavior. They help the team narrow in on likely pressure points earlier in the design and reduce the time between exploration and implementation, so that by the time a new core is released, it has already been shaped by this entire process. It has been modeled against the workloads expected to run at launch and tuned to expect software evolution built with input from the customers who will actually deploy it. This makes it easier to integrate. It also reduces the risk that something fundamental will need to be reworked once silicon is committed. Now, ARM refers to this entire process as its workload-driven design, several decades in the making. It treats software insight as a first-order requirement to its back end and builds hardware to match with what the system actually demands. To that end, I caught up with Fred Piry, the lead CPU architect and fellow at ARM, to get his download on what needs to be in place to make a good CPU design great.
The way we help software developers, I think there's multiple things. For some, what matters is a new version of the architecture, so new instruction, new feature in the architecture. So for that, we deliver very early models that can be used to develop software with early version of the compiler. For other partners, it's more about tuning their library. So we work with them to understand what are the important part of the software stack that we need to optimize for, and very often it's collaboration. So we co-optimize the libraries and the part of software that matters most for them. AI, and AI, but beyond that, power efficiency is still what matters across the industry, whether you're talking to infrastructure customers or to mobile people. That's the same. Power really matters. And I think security comes second maybe, or maybe it's on par, but people do care a lot about security, whether that's from the architecture itself, so security features that comes from the architecture, or security from the implementation, so what can be tricked in the way we implement the ARM architecture. But very often we have to adapt the feature we develop into the process our CPUs will land in. And very recently, the move to 3 nanometer has been harder than expected, meaning that we have to revise which features we were going to implement in the CPU that intercept the first version of 3 nanometer. So yes, it happens. And this collaboration and relationship with the foundries is also very helpful for us to predict what we can land versus what we cannot afford to land.
ARM's customers also demand tight security enablement in the architecture. ARM's MTE, known as its memory tagging extension, which acts as a powerful debugger during system bring-up. In deployment, it can enforce memory safety live, stopping issues like use after free or buffer overflows as they happen. In 2021, ARM built on this with enhanced MTE, which adds additional options such as store-only checking. Now, ARM's early reputation came from its CPU cores. Today, those cores matter most when delivered as part of a fully usable system. Cores are most useful when the entire system around them is accounted for, and ARM has reorganized to support exactly that. The company now delivers something called CSS, or a compute subsystem, which serves as a foundation for a complete compute platform. Now, I've been hearing about CSS for a couple of years, but the idea is to provide a validated, ready-to-integrate system, not just blocks of IP. It brings together the CPU core, the interconnects, the memory controllers, coherency logic, and debug tools. Alongside that comes firmware, drivers, and the low-level software needed to boot and validate real hardware. All of this is delivered together, tested together, and versioned together. That gives the chip companies who take the CSS a complete starting point with major components already integrated and tested. Now, one common misconception here is that the CSS is a complete layout that a customer can ship, but actually each customer can optimize for their ideal configuration point. We're talking core count, caches, power, but also the add-on IP in order to complete the chip, because it's not 100% complete without it. What matters here is that most of the parts are pre-validated, saving time. ARM provides the validated ingredients, but it's up to the customer to actually bake the cake, or if they want to add in or take away any of the ingredients. So CSS actually now spans multiple product categories. It was initially first in the Neoverse CSS, and it appears in things like Microsoft's Cobol 100 and AlphaWave Semi's data center chip. Client CSS targets personal devices, including laptops and phones. The automotive CSS, called Xena, includes functional safety logic and serves designs that must comply with standards like ISO 26262. Xena supports that real-time compute where determinism and tight latency control are central. These designs are already in flight with real customers and backed by concrete product plans. One of the major benefits here of CSS is the ability to shorten development cycles. By having a well-integrated base platform, you can enable performance tuning, software bring-up, and system validation earlier in the development process. This means things like AI-specific extensions in a core, like SME2, can come built in with toolchains and firmware support already in place. That makes it possible for customers to experiment with new workloads on a platform that will behave like their production hardware. Over time, in the long term, ARM believes that this approach builds a stronger ecosystem. Developers can reuse tools across their CSS-based designs for future efforts. It means chip makers can adopt newer core generations with less ramp-up time and iterate quicker. The thing is, CSS as a whole just marks a fundamental shift in how ARM collaborates with its partners. Rather than developing discrete IP blocks, the company now supports full systems, shaped in concert with the teams that use them, and further optimized by customers down the pipeline. This focus has moved towards delivering cohesive platforms where design and integration happen alongside each other. Now, there are many ways for companies to work with ARM. There are simple licensees who don't use CSS, they just use the cores. These are often referred to as TLA customers. They take ARM's CPU IP and handle everything in-house. You can also take the architecture and build your own. These are called architecture licensees. As of mid-2025, ARM has over 40 architecture licensees and over 350 core licensees. Companies like Apple, Samsung, and MediaTek have been very successful. These are typically experienced chip makers with their own design flows and tool chains. They value flexibility and often build fully customized systems around the cores that they use. The thing is, CSS here supports a different type of engagement. It gives customers that validated foundation, including infrastructure tools and scheduling alignment, but also it enables a form of technical co-development. Architecture teams at both companies, ARM and its customers, can track the progress together, resolve bottlenecks sooner, and share visibility into roadmap alignment. This process is already active with all the major infrastructure players. Their teams contribute datasets, simulation runs, and real workload constraints. The feedback is specific to the design and to the CSS. It covers, as I said before, instruction mixes, latency targets, thermal budgets, and integration requirements. By using CSS as that base, ARM can incorporate those details into early prototypes and evaluate architectural choices under real conditions for future platforms. In many cases, those partners are also involved earlier in the design cycle. While the CPU core remains an ARM product, the surrounding system often reflects decisions made jointly with customers. That same design may be tuned across multiple generations or used as a base for a more customized effort later on. The working baseline allows faster validation, software bring-up, and firmware development. So while ARM supports flexible licensing across its spectrum, CSS has actually become the key part of how it builds its long-term alignment with its partners. Architecture and integration evolve as a single process, not as separate ones. I managed to spend a few minutes with Chris Bergey, the SVP and GM of ARM's client business, while I was at the headquarters, to explain why ARM CSS is developing into a hit with its customers.
So I think customers are looking at, they're facing a lot of challenges right now, right? They've got to go fast. They've got very short development cycles. We're all dealing with the costs associated with delivering next generation ICs. And they want confidence that it's going to work the first time out of the box. And so CSS provides value around all of those different vectors. Well, I think ARM has over 30 plus years, has been known for building a tremendous ecosystem of IP and tremendous IP deliverables. We have now brought into the company capabilities in building silicon and really optimizing that all the way to the transistor. I think if you look at the amount of companies that can build an amazing RTL and IP blocks and highest performance CPUs and optimize them all the way down to the transistor, There's a very, very short list of companies that can do it. And we think we not only do that well, but we have the advantage of doing it on the world's most pervasive architecture in support of our over 22 million developers that develop software on the ARM architecture. So we have delivered over 25 mobile CSS blocks at this point in time that are being integrated into different SOCs and different areas of deployment. Some are available for sale today. I think for ARM, we've always been about partner enablement and really ecosystem enablement. And the amount of AI that is being built on ARM is incredible. And so I think it's that combination of the AI revolution and it being built on ARM is a tremendous opportunity and responsibility for us. And so it's really, how do we seize that and take advantage of this next computing revolution?
So let's talk about data center for a second. Because the thing is, some of the largest machine learning data centers on the planet already run a lot on ARM. The AI boom has driven enormous demand for accelerators, and those accelerators still need a host. Every GPU, every AI engine, every inference card is practically managed by a CPU. And in many of the most advanced systems, those CPUs are ARM-based. That includes majorly NVIDIA Grace, but also Amazon Graviton and other hyperscaler designs. These systems are deployed at scale, generating real revenue and handling control, scheduling, and telemetry for AI inference and training. They're winning out over incumbent x86 designs left, right, and center. That role comes with tight constraints, because if the CPU burns too much power or bottlenecks data flow, the rest of the system can't operate efficiently. That's what ARM delivers here, predictability. Partners know the performance profile before the chips come out. They know the power budget, they know the reliability across the workload before they have their hands on the silicon. That's essential for building systems where the CPU is expected to run constantly in the background, managing everything else. Now that model really applies beyond the data center here. AI runs on phones, inside cars, in factories, in edge boxes bolted to walls. ARM already appears in all of them. It's the same fundamental architecture adapted to the form factor and performance envelope. That continuity means developers can reuse tools, compilers, and software assumptions. It simplifies design. It means that a unified architecture doesn't mean one-size-fits-all core, it means that the design philosophy travels well. From the lowest power embedded devices to the largest server racks, the CPU is expected to maintain coordination. That's memory movement, interrupt handling, things like secure enclave work, and fallback execution when the accelerator can't take the load. So even as AI hardware itself is becoming more specialized, the CPU is still the point where things are managed. If it fails, the system stalls. That's why CPU design remains central. Everything else builds around it. Now, with all the different ways a CPU can perform, how can we actually spot a good CPU from a bad CPU? Clock speeds and core counts still show up in the marketing, sure. And we learned a while ago that that doesn't tell you how a CPU behaves in the real system. Modern designs are judged on how efficiently they manage the work across a range of conditions, especially under thermal and power constraints. In AI platforms, where power is often a limiting factor, performance per watt and ASIC utilization are metrics that matter a lot more than most. Hardware that can enable those scores, the highest marks, wins out. Responsiveness can also be just as important. A strong CPU keeps the latency low, it coordinates with accelerators, and maintains a flow without bottlenecks by orchestrating the data. That comes down to coherency, caching, memory bandwidth, and how well the scheduler handles bursts of work. Flexibility is another key marker here. A CPU that runs well across different software stacks, kernels, toolchains, and OSs offers a broader return. That includes how it interacts with system firmware, how it handles those interrupts, and how easily developers can build around it. You don't see this in synthetic benchmarks as much. Most of them ignore real I/O paths, thermodynamics, and memory contention. Those gaps matter more than the peak number on the box. I've said it before already in this video. Delivery schedule also changes the equation. A chip that ships on time and integrates smoothly will see more real deployments than one with better specs that arrives late. Developers in AI right now are moving super fast. Systems evolve quickly. A CPU earns its place when it shows up at the right moment with enough support to be built forward. For companies building their own, it can make or break their value proposition if it's not available at the right time. So having the right infrastructure in place with the right partners is a key attribute. Now, I spent the full day at ARM headquarters talking to the architects, the system leads, and engineers across the stack. I've watched how real workloads get modeled and sat in meetings where CPU design isn't just about drawing a very pretty block diagram in a CAD tool. It's about engagement. It's about knowing where the software is headed in 1, 2, or 3 years. It's understanding what customers will need and what they'll actually use. There's no longer any room to provide something that's good enough, especially when you're in the market for shipping 50 billion CPUs a year. Having a streamlined process, having that go-to-market strategy with something like CSS, for example, is one way to enable the industry with performance at scale at a regular cadence. It won't be the route that everyone takes, but it's a route of least friction that provides a top-tier design built on the back of hundreds of ARM hardware users and software developers. That's something you can't get in your academic building an open source core.